Beneath the surface of Texas are extensive water-bearing geologic formations that make up the state's vast and diverse system of aquifers. These aquifers provide more than half of the water Texans use each year. Aquifers are rarely underground lakes like you might see in a cave. They are typically rock formations that are mostly solid, but like sponges, they have interconnected fissures and pore spaces that hold water and allow it to move within the formation. An aquifer is best defined as a layer of saturated rock and the water in its pores. Aquifers are formed very slowly over vast periods of time. Water in aquifers comes originally from the surface of the earth. When rain falls, some of the water infiltrates underground and collects in the pore spaces. Water in rivers and lakes can also seep into the subsurface pores. Eventually, some interconnected pore spaces become saturated with water. In other words, they become an aquifer.
The ability of an aquifer to produce water depends on the properties of the aquifer's rock formation. The two most important properties are porosity and permeability. The porosity is a measure of the volume of empty space, or pore spaces, inside the rock. Pore spaces can be openings between grains, fractures in the rock, and even caverns. Porosity represents the volume of water a rock formation can hold. Porosity itself isn't enough to create an aquifer. The areas filled with water must connect with each other so the water can flow from one pore space to another. That connectivity between pores is known as permeability. Permeability is a measure of how readily water can flow within the rock. Rocks such as pumice and shale can have high porosity, but do not form productive aquifers because the pores within the rock are not connected. The permeability of pumice and shale is low. On the other hand, gravel transmits water quickly because of large connected pore spaces. The permeability of gravel is high.
Compared to water movement through rivers or lakes, the rate of movement through an aquifer is slow. Of the 9 major aquifers in Texas, 6 of them, the Ogallala, Gulf Coast, Carrizo-Wilcox, Pecos Valley, Seymour, and Waco-Mesilla-Bolsons, consist of sedimentary rock with relatively high porosity and permeability. Sedimentary rocks are composed of sand, gravel, silt, and clay. The 3 other major aquifers, the Edwards Aquifer, sometimes referred to as the Balcones Fault Zone, the Trinity Aquifer, and the Edwards Trinity Plateau Aquifer, consist either mainly or partly of limestone. Water in limestone aquifers is held in crevices and caverns left by the dissolution of the limestone by groundwater. This subterranean landscape is known as karst, and it is highly permeable. Being on a fault zone, the karst limestone of the Edwards Aquifer is highly fractured. Rainwater seeps very quickly into the Edwards Aquifer through the fault lines, even while a storm event is happening. Not all limestone aquifers in Texas recharge this quickly.
In nature, aquifers are seldom separated neatly into geographic areas. Instead, like a stack of pancakes, aquifers overlay each other and dip at different angles. Some parts are exposed to the Earth's surface, while other parts are buried under other aquifers. The part of an aquifer that is exposed at land surface is known as the outcrop. The part that is in the subsurface is known as the down-dip extent. For example, the outcrop of the Carrizo-Wilcox Aquifer is a narrow band that lies parallel to the Gulf Coast. As we move towards the coast, the aquifer slopes beneath the land surface, forming the down dip. Aquifers are separated from each other by aquitards. Aquitards are impermeable layers that prevent water from easily flowing from one aquifer to another. An aquifer is confined when it is buried beneath other aquifers and/or aquitards. The combined weight of the rocks and water above pressurizes the groundwater. This is sometimes referred to as artesian pressure. When the aquitard above a confined aquifer is punctured by drilling a well, Artesian pressure causes the water in the well to rise. Sometimes this water reaches land surface, resulting in a flowing well. Springs are water flowing to the surface through natural pathways caused by the faulting or dissolution of aquifer rocks. Pumping in a confined aquifer causes the pressure of the groundwater to reduce. The reduction in pressure lowers water levels in artesian wells and springs. Because confined aquifers are, by definition, not always well connected to surface water sources like streams and lakes, recharge may be slow, if it happens at all.
When an aquifer is exposed to the Earth's surface, such as at the outcrop, it is unconfined. The groundwater is not pressurized. When we pump an unconfined aquifer, it lowers water levels in the aquifer itself. In addition, because the water is not under pressure, it takes more energy to pump water out of the aquifer. Unconfined aquifers are usually replenished more easily than confined aquifers because rainfall and water from rivers and streams can flow into the exposed areas of the aquifer. In addition, the material above an unconfined aquifer is usually porous, so surface water can seep into the aquifer.
The better we understand the geologic properties of aquifers, the better we can understand their sensitivity and susceptibility to human use, such as pumping and contamination.